So, thank you for being here. My name is Guilherme, and I'm representing QUCS, the Quite Universal Circuit Simulator. As a side note, the first name was actually Qt from the Qt framework, but they got a message that, well, it's not related to Qt, please change the name. So they changed to Quite Universal Circuit Simulator. So my talk is about an overview and the status of the development and some remarks, and if time allows, I will show you a short demo of what the tool is about. So the project started in 2003. It was created in TU Berlin by Michael Margraf and Stefan Jan. The first one created the user interface, the second one created the solver or the engine. It was from the beginning GPL 2+. To date, it has more than 20 contributors. It's translated into about 20 languages. It's cross-platform. And the user base is varied. It's from education, from researchers, hobbyists, and even the industry. You have some stats here for the website that was there from 2005. Number of downloads. This is from SourceForge, where the code is hosted since the beginning. The binaries and the source, the tarballs. And on the graph below, we have the count for Windows binaries that were released like 13 days ago. So we have roughly 400, 300 downloads weekly for this part with the Windows binary. And I mentioned that the original creators, they are no longer active on the project. Around 2011, 12, they dropped the project, so it went orphaned, and the community adopted it. So the main features, it's basically a schematic capture, a simulator, and it has data visualization built in. It has an equation system for pre and post processing of the signals. It has a component library, which is also parameterized with common components, and it has also design and synthesis tools. For modeling, if you want to write models, it has some feature to import SPICE netlists. It's quite limited on the constructs that it can handle. It has a built-in component that's called equation-defined device, which is quite powerful because you can really rewrite the equations for, say, a transistor model in this kind of even graphical fashion, which is quite handy for development. And it also has a Verilog A model builder or loader, and it has some post-processing capability that you can export data in NuCap or Python or Octave. And the dependencies that we have, it's C++, Qt 4. We're still struggling to remove Qt 3 from the source, but we are working on that. It builds with AutoTools and CMake, and Jupyter for the simulator, and the parsers are also written in FlexBison. We depend on ADMS for the Verilog A part, and the documentation, most of it is written in LaTeX. There is some experimental work, or I would say external work, that's not in the main line, which is this fork. It's called QUCS, which is by Vadim Kuznetsov and Mike Brinson, the first one from Russia, the second one from UK, which is a pretty full-featured SPICE front-end based on the QUCS schematic capture. It can work with ngSpice, Zeiss, and SPICE Opus. They made up Verilog A generators that work with these equation-defined devices that you can make your device graphically and then generate a Verilog A code. They also made recently some extensions for xSpice, so they can also, in a similar fashion, make C code that can be linked into ngSpice, for instance, and SPICE Opus, I guess. The previous speaker, Felix, mentioned GNU-Xator, which is one effort that he started to make a replacement engine based on GNU-Cap for QUCS. And there is also one effort that we saw this year. This user, he has a tool that translates into GSChem, and he managed to import the schematics from QUCS into GSChem. So that's interesting. So for support for the project, we have the main website. At the moment, we have, I count 6 active maintainers or developers. It's me, it's Claudio, that's in Italy, Vadim in Russia, Felix, that's here, that's located in UK now, but from Germany, Andres, that's in Spain, and Mike Brimson, that's in UK. We have, I think, it's a quite good documentation, especially the tutorials and the technical manual. You can find on the website. They are very well written and cover quite a lot of ground. We have, a traditional, we have most things on SourceForge, for example, the binaries. We have the Git repository, but we are gradually phasing it out in favor of GitHub. We still have the issue tracker enabled there, and the forum is sometimes active, and the mailing lists are also hosted there. On GitHub, most of the work is happening there now, and most of the issues are also there. We ported the wiki from SourceForge when it was disabled into GitHub. And from there, we also enable continuous integration with Travis and AppVeyor for Linux, OS X, and Windows. So if you look into the package, what kind of tools do you have there? As graphical interface, you have QUCS, which is the schematic capture. And then you have design tools or helpers that is for active filter, attenuators, passive attenuators. It has a built-in editor that we are phasing out as well. It has a tool for developing passive filters. There is a small help tool that's being also phased out in favor of read the docs documentation online. There's a matching tool. There is the library. And there is a small resistor to color conversion codes that's useful for students. And there is also a transmission line calculator. In total, we have, now it's less, but it was 170 components. We removed some non-GPL components recently, but it's we are adding new components for RF, so the count is about the same. From the command line, you can access QUCS, which is the interface, the schematics. You can use the QUCS which is a simulator, and QUCSconf that converts between formats, also imports the SPICE netlist into the QUCS native netlist. And we also interface to third-party tools like ASCO, which is an optimizer, ADMS XML, which does the Verilog A to code or C++ conversion that we need to run the models. We can run from the schematic Verilog, FreeHDL that we are working to replace by GHDL, hopefully for the next release. And there are some conversion tools from PSpice to Spice. And then you can also run, there is a doc where you can run Octave directly from the user interface. And Python is mostly scripts, so for parsing the data. I will show quickly these screenshots, but I also do a demo in the end. So this is the main interface. You have on the left, you can have many projects as one. This reflects your working directory. It's synced with the file system. You can have different contents for each project. And then on the right, you can have either circuits or inline visualization, or you can have also separate tabs only for visualization. So you can make quite nice looking documents to document your simulations or models. So we have a component tab where you can drop down most of the built-in components. And you have libraries which are either SPICE-based or parameterization of the built-in components. And yeah, as I said, you can have a nice separate documentation or visualization tab for documenting, if you like, or simply to look good. A few of the tools, this is merged on the latest release. It's for developing or designing active filters. So you input the parameters, and then it visualizes for you the schematic. And then on press of calculate and copy to clipboard, you can just paste it into your schematic and have it running on the simulator. Similarly, you have these passive attenuators. So there is a whole range of topologies that you can input there and get the schematic ready for simulation. We had that, which is the help, very simple, like introductory help that's now migrated to that website. This is going to be removed. Then we have also these matching ports that Then you have the library where you can drag and drop the components from this dialog or from the doc that you have on the user interface. And this is the calculation from colors to value or value to colors. It was okay. Then you have transmission line calculation. There are new components that are coming on for the next release, but it has a dozen of components that can be already now used for transmission lines calculations. Then you have also these passive filters. And as I said, what can you do? You have what can you use from the command line? So the user interface can be used for generating the netlist from a schematic. It can also print the schematic. And there are some commands to dump the components that we have. So this could help if you are looking into extracting the component descriptions. You can hack into that to do it. The simulator supports DC, transient, AC, S parameter, and harmonic balance is just for resistors, capacitors, and inductors at the moment. I highlighted here S parameter because this is, to my knowledge, one of the only tools that does that on the open source. It's directly, right? You can do with AC simulations, but this is a built-in feature of the tool. That's it's where it started also. The first commits of the simulator and the user interface were to accommodate S parameter. And the QUCS is a tool that converts between a few formats that are used to visualize or to convert netlists and library components. And yeah, this is a bit of the problem that we might talk later on the panel, that we have custom file formats for the schematic, which is the same for the library, and also the netlist and the data files. They are plain text files that are also custom. So we might work on that to collaboration. It's a bit difficult. It makes more difficult because of that. Okay, on the front of Verilog A, we had quite a lot of models. We still have quite a lot of models. However, due to licensing issues, we had to remove 3 of the industry standard models. They were a bit like BSD 3 clause licenses, which are incompatible, and we stripped them out from the repository. We are now moving them to a non-free repository. We got a bit of a backlash from the model developers, but there is nothing you can do. It's incompatible. We removed. Same thing with ADMS. There were headers that were proprietary to Accelera, which is the organization that handles the standard. So me and Felix, we stripped those headers and we rewrote new headers, and we relicensed ADMS as a GPL 3+. And yeah. Concerning Verilog A and QUCS, there is a limitation that this construct is not yet supported. But for most things, you can compile BSIM6 and some other very complicated models. Okay, they run slowly because our engine is kind of slow, but it runs, and it's mostly accurate compared to commercial simulators. We might have to compare against GnuCap now. So. And okay, I have a demo, but I will just close this slide, so I will go as time allows to the demos. These are the same demos from last year, but just for the ones that are here to get a feeling of how the tool behaves. So I have this circuit with a parameter sweep, a macro model, optimization. That's a kind of thing that would be interesting to see as an output to a layout tool, because these microstrips are basically traces on a PCB or another substrate. So this is something that we could work with a layout tool to get it exported. That's quite interesting. So how you can do some Verilog and VHDL simulations. And okay, to wrap up the slides, 19.19 was released. Mostly bug fixing, cleanups, ongoing porting from Qt3 to Qt4. There is this new tool that's the main new thing that we have. We did integration, a bit of regression testing. We removed the non-GPL we adopted a new Git branching model, because before that we were merging everything into master, and it was kind of untidy. Now we have master only for releases, and we have develop for development. And on this release cycle, we closed roughly 160 issues, regressions, and things like that. For the next release, we coordinated a bit better the efforts, and we are prioritizing some RF components and microwave components that were developed by Andres. And there is also a tuner feature that you can slide values and rerun the simulation. As I mentioned, removal of QUCS editor and QUCS help. We hope for a quick release, but there is also other things that are on the pipeline, like Felix is implementing a way of loading similar to GNU-CAP things into the user interface, which might help us on the future. And this is the status for the development. And okay, I just put it here for the PDF. You have all the links you might want here. This is also interesting. We are now getting more and more translations on this translation platform, which is nice, because then helps us on localization of the tool. And the final remarks: the project as a whole aims to be very user-friendly. We have advanced components and modeling features. We are open to collaboration. We hope to, use more the tools that we have available and enter into the working flow of more people. And your help is most welcome. I do have a few examples I would just show. So as I mentioned, we have this tab here with the projects. Then I have 5 minutes, right? Just show one example. So ideally, you pick up your components from here. We have a library of components, but this is already configured. So we have on the contents this schematic. I will close this now. So, yeah, this is a simple example where you can enable and disable parameters like that. So in this moment, the value of this resistor is being picked up from this equation. These equations can be quite complicated. They are pre-processed and then sent to the simulator. And then you can run this NAC simulation. You get a short transcript of the solver. And then just like that, you can toggle that parameter into a parameter sweep and then rerun it. And then you get this visualization online here. I will show you maybe another project. This I will skip. This is the one I mentioned about microstrips. So this is perhaps not the best frequency. This is for 10 gigahertz, but you can also do microstrips at lower frequencies that can be easily manufactured on PCBs if you want. And this is something I would like to see pushed forward on the layout side. So, and it's quite quick to run. So this is the SP parameters of this bandpass filter. Dock window. Then we have the intention, this is a Verilog. It can also, so in this case we have this Verilog file here. And here you have the description of the Verilog. Then it wraps it into a test bench and it ships it to Icarus, and then you can run it. Yeah, it has some warnings because the wrapper is not properly done, but then you have the counter here. It's visualized here. I have to fix this. Never tried a small screen, so. And a simple example of Verilog A. Here we have the equations defining RL a resonating tank. Because we don't have the V assignment, we do a trick here to transform the inductor as a gyrator, but that's beyond the point. And then you can basically build this model. So it's going to kick in ADMS in the background, generate C code, C++, then run the compiler, and then you predefine the symbol for this text. Then you can load it, and you can assign an icon to it, and then you can now open the schematic. Let me full screen this. So here you have the equivalent into primitives, and here you have the equivalent from the Verilog A, and then you can just run it. Then it runs some warnings, and yeah, it is just the error from the two curves. But this is the idea is to have a very streamlined workflow to load components into the user interface as well into the simulator. But that could be streamlined further because these manual steps, they're not necessary. As Felix showed before, we can have commands on your netlist that make this machinery all into the simulator itself. So we are working to either replace that or to streamline this process. So as a closing note, QUCS is about schematic and simulation. We don't have any PCB. We don't have the concepts of footprints. So to do that, we have to interact with other projects. And if you want to see that happening, please help us. So if you have questions.
Questions? To what degree your netlist format is compatible to SPICE? Is it one-to-one, or what's the benefit of having your own netlist format?
So the question is, to what degree our custom netlist is compatible to SPICE? It's not. It's a different format altogether. Worse than that, our components are primitives of our simulator. Our components or the models are only available at the moment. Some of them are only available into QUCS. So if you want to run that into a SPICE-like, you have to first move the components to a SPICE engine. So it's a dual problem. It's not only the netlist description, but also the availability of the underlying models that are not there. So, yeah.
Questions? Can you work with vendor models of OBAMs or something like that?
So for the question is if you can use vendor models. That depends. If you can import SPICE descriptions, sometimes you can translate into the built-in components of QUCS, then it works. But as long as you have more complicated SPICE descriptions like those some poly functions there, we don't have the conversion built in, so that will not work. So for simple models, yes. Yeah.
Do you have a release schedule for removing the Qt support?
The question is if we have a schedule for removing the Q3 support. No, because we work on our free time. So the release is ready when it's ready.
But it's priority?
Not for the next release. The next release is a short one. It's mostly for merging these RF features that Andres needs for his work. So maybe for the next release, I have an experimental branch where most of these Q3 things are removed, but they need work. They need work. They need fine-tuning. So maybe 1 year. Yeah.
Can you share what those RF and microwave tools are that you plan to add?
Can you repeat the question?
Can you discuss those RF and microwave tools that you plan to add in the next release?
So the question is, what are the tools for RF and microwave that are going to be introduced on the next release? I don't know them all, but I know that there is a tapered waveguide. There is a circular transmission line, cylindrical transmission line. There are mostly new components. There are no new tools, so to say, but there are new components that are going to be integrated.
Going from the sort of strip-line models you were looking at with saying PCB export would be useful, how much would it take to get from where you are now to having a sort of transient signal integrity simulation? And what kind of data do you need from
So the question is about the microstrips. What would it take it to make a transient signal integrity simulation like? Most of the RF components, they are only defined in frequency domain. So you would have to have some way of converting that back to time domain. So that's not there.
Okay, so if you extracted some layout from the board, you could do at least an RF simulation.
So the question, if you extract parameters from the board, if you do a S-parameter extraction, you could do signal integrity analysis, for instance. You could do if you want to evaluate the signal integrity at the pins of your chip, and you did the extraction of that, you get a S parameter or then you can do signal integrity on that. I saw people from the industry doing that, just that. One remark, we had a request to increase the number of ports on the SP files that we could handle just to run this kind of simulation on these multi-pin chips that are out there.
As a student, my main question is, why would I invest time in learning QUCS instead of spending time on just standard SPICE? What does QUCS offer me that SPICE will not?
So the question is, why invest time in QUCS instead of using SPICE? Note that SPICE is the engine, right? So there is a divide between the schematic entry and the engine, right? So, if you want to really, that's also a problem for me. I don't want to be, this black hole where you dump your schematics, your knowledge, your IP, and you cannot get out anywhere, right? So, at the moment we are working together to have this to be able to port one schematic to one project or another, as it should be, right? But what can I say? If you need the tools that we have, maybe other tools don't have it. Like the modeling capabilities that we have, for research, it's interesting. So as a hobbyist that you need to get the models from the internet, maybe is not the best use case. But yeah.
We're running out of time, but I think this will be a subject of discussion in the discussion session after the next talk. So let's thank Guillermo again.
Thank you.